When a client needs a flat building pad carved out of a naturally sloped hillside, the Earthworks contractor must step in and reshape the land. But before machinery moves, estimators need to know exactly how much dirt has to be removed. This determines how long the job will take, the size of the equipment required, and the overall cost. This spreadsheet shows the standard industry workflow used to find that number. It's called the grid method, and it converts raw topographical data into a precise cubic volume. Getting the math right here is what separates a profitable Earthworks quote from a catastrophic miscalculation. This site plan shows a topographic grid where every peg gets a unique alphanumeric address. Laid over this are contour lines. Every point along the 114-meter contour sits 114 meters above datum. The even spacing up to 116 indicates a steady, predictable slope. Understanding how the existing land rises and falls across these known coordinates is step 1.
Next, we have to figure out where our flat building pad will sit inside this terrain. The dashed yellow line represents our proposed excavation boundary. The complication is the pad doesn't align with our survey pegs. To estimate a pure cut down to the target platform, we must first calculate the starting ground elevation at these 4 boundary corners. We use interpolation. Locating the nearest known elevations, the 112-meter contour and 112.7-meter peg, we draw a working line. The rise is 0.7 meters. Sitting 1/10 up the slope, we divide 0.7 by 10 and add the baseline, establishing the corner height at 112.07 meters. This process is repeated around the perimeter. Every single corner of our excavation must have a hard numerical value assigned to it before we can move on to measuring the volume. We break the excavation zone into independent 3-dimensional prisms. Subtracting the platform level from the surface elevation at each corner gives the exact cut depth. Averaging those 4 depths, we multiply by the base area to calculate the block's total cubic volume. Doing this math for one isolated block is straightforward, but running that exact calculation independently for 50 or 100 prisms across a large site is incredibly tedious. We need a faster system. This diagram demonstrates the shortcut. Because the prisms are connected, most grid pegs do double or quadruple duty. A peg on the outer boundary might touch only 1 or 2 prisms, but an interior peg is shared by 4 surrounding blocks. We lock this data into a table. Multiplying each spot height by its number of uses gives a collective excavation depth. Dividing total collective depth by total uses provides the average depth. Multiplying that by site area reveals the total cut, 847.6 cubic meters. It is crucial to remember that this result is the bank volume, the physical space the dirt occupies while still packed tightly in the ground. Once an excavator digs it up, the packed soil expands, increasing in size to what is known as loose volume. If an estimator quotes haulage based solely on in-ground bank volume, they'll order too few trucks, leaving unbudgeted loose dirt sitting on site and eroding the project's profit margin. This completed spreadsheet represents the final output, moving from raw topographical surveys and site grids through corner interpolations directly to an accurate bulk excavation total. Because the math is laid out systematically, any unexpected numbers can be audited and traced straight back to a specific peg on the field plan. Once you construct this grid logic in your software, you don't have to build it from scratch again. You simply drop in the new site data, and you have a mathematically proven template for every Earthworks quote going forward.